My name is Andre, and I'm the acting head of Malm Technologies. Now, as you probably might have noticed if you've been in this conference for the past 2 days, Malm Technologies is a software company which is dealing with computer vision and artificial intelligence-driven reality capture, and also with 3D data fusion, virtual landscape streaming, and rendering. Now, the topic of this talk is alien worlds, 3D maps of celestial bodies with VDS. And the first thing that I think is worth answering is why celestial bodies? And let me ask you a question. Is there a planetary scientist around here? Oh, well, good to see you. Anyway, I think it's fair to say that if you're a GIS professional, then planetary science, celestial topography, and nomenclature of celestial bodies probably is not your day-to-day business. So, but still, there's a reason why you're all here. So let me wonder about it a little bit. I'm, of course, tempted to say that celestial bodies and planetary GIS is interesting to all us, because simply space exploration pushes the envelope of science and engineering in general. But I'd like to take like a more partisan view in the scope of this conference, why planetary data deserves our attention. And first of all, it's a very open and democratic data domain. It's probably fair to say that in space exploration and planetary GIS, open data was prevalent decades before it became prevalent in terrestrial GIS. Space exploration is being paid for with taxpayers' money, and that reflects on the nature of the data that we're dealing with. So that would be reason number one. Then there is the wide availability of the data. Like pretty much any sensor data ever collected is available to you, and there's very little obstacles in reaching it. You have stuff like NASA Planetary Data System, ESA Planetary Science Archive, where you can download the raw data. You have lots of third-party ancillary data products which are available either from the USGS Astrogeology Science Center or from a network of collaborating government agencies and universities. And last but not least, there's a very heavy tradition of free and open source software-based data processing connected to extraterrestrial remote sensing. So I find these reasons compelling. But perhaps there is one more, which is even more important to me and to Malm Technologies as a company, and that is that our ability to work with extraterrestrial data is a very important test of the generic and abstract quality of our data design. I'm not perfectly sure if I'm understandable in this, but somehow I have a knack on abstract high-quality data design, and I somehow feel that if our data design fails outside the terrestrial domain, chances are it's going to fail inside it as well. So once we started to design the VDS geospatial software stack, we were very much focused on making this generic and able to work with planetary data. The goal in this talk is to provide a hands-on demonstration of celestial bodies 3D mapping using solely open source software and public domain data. And to this aim, we are going to have basically 2 case studies as a vehicle. One is going to be the virtual reality experience in Copernicus Montes on Mars and New Horizons 3-dimensional model of Pluto. Moving on to the first case study, Copernicus Montes is one of the most striking topographic features in the entire solar system. It's an equatorial, it's part of the equatorial system of canyons, which is known as Valles Marineris. And we're going to try to create a virtual reality experience inside it. Regarding the second case study, even if you're very remotely interested in space exploration, I'm sure you have not missed the flyby of the Pluto current system in 2015, almost exactly 3 years ago, which provided us with some astonishing data, such as this image, which became collectively known as the heart on Pluto, and which has been taken by the long-range reconnaissance imager, one of the instruments on board of New Horizons. And we're going to somehow try to take this image, and actually lots of other images, and to turn them into a browsable 3-dimensional model of the dwarf planet. The technology which is going to allow us to do all this is the VTS3 geospatial software stack. We're going to use it heavily, map proxy for dynamic TIN generation, VTSD and VTS command line tools for server-side data fusion, and also the VTS front-end rendering libraries. I've written here VTS browser.js, meaning the JavaScript client, but we can take a look at the C++ desktop renderer if we have time in the end as well. Why VTS? It's fair to say that this is not the only way to do it, the one I'm presenting. There's projects such as MarsTrack and VestaTrack, which have been very successful and based on cesium technology. Also, you could probably do stuff like this with Google Earth, and derived products. But there's compelling reasons why to use VTS for this purpose. First of all, it's the coordinate system agnosticism. You can deal pretty much with any coordinate system and pretty much with any object in VTS. Planetary modeling in VTS is purely declarative, meaning that you do not need to write any code to model the planets. VTS also supports complex frames of reference, which is somehow a complex topic by itself, but it means that you can actually combine different spatial reference systems within the same tile hierarchy. And this leads to interesting effects such that there is no inherent polar cap or dateline issues, which I'm sure you're well familiar with if you're working with any type of global data set. Now, I do not have possibly enough time to cover every possible detail of this case study in this 20 minutes, or better say about 14 remaining minutes of this talk. So I've set up this accompanying site where you can find live demos of everything that we'll be doing, details, configuration, tab files. Feel free to take a look at it even as we talk right now. The amount of information presented there might be a little overwhelming, but we'll try to make sense of it. You need mine to? Okay. As a prerequisite for these case studies, we need a functioning VTS backend, which is a pretty easy thing if you have a mainstream recent Ubuntu distribution. And yeah, that's it for the prerequisites, and we can move on to our case study number 1, which is the virtual reality experience in Copernicus Montes on Mars. Now, we're going to be needing some data. Well, that's a surprise. The first data ingredient is we're going to be using the Mars Global Digital Image Mosaic, which has a ground resolution of 231 meters on the equator, and it covers the entire planet. It's based on the original data from the Viking probe. And we're going to be using the Mars MGS molar elevation model, which has a ground resolution of 463 meters and is also a global data set. We'll be using the Mars nomenclature to make some sense of the unknown alien terrain. And we'll be also using the Mars Express HRSC image of this number. That's like local data. All of these data sets were global. This one is local. And it covers a strip which is about 75 kilometers wide and 290 kilometers long in Copernicus Montes. And it's got a ground resolution of 12.5 meters, which makes it interesting enough for terrain exploration. And to have even more detailed data, we'll take a look at the Mars Reconnaissance Orbiter high-rise stereo pair, which has an astonishing ground resolution of 0.5 meter in GSD and 2 meters in geometry. It's for a small area, 4.6 by 15 kilometers, but it should give us the view of the surface of Mars in a local view, but a view in unprecedented detail. This is the best data available. Some of these data sets are provided as public VTS resources by Melon Technologies, so that's going to make the setup a little easier. We start up with creating the base map of Mars. We create the base map of Mars by adding the molar elevation model to VTS storage. So this is this simple command. After we do this, we set up so-called VTS storage view, which is basically a JSON file which contains a configuration for our map. And inside this file, well, we make use of the DEM which is added to the storage. And we make use of another VTS public resource, which is that global MDIM 2.1 mosaic I was talking about just before. So we have basically a map which has two resources, a TIN service from the DEM and then orthophoto imagery service, tiled map service. We did not need to set these two up because they are provided as public resources, so we just refer to them. It would be perfectly possible to have this whole thing self-hosted, but this is the easiest way to set it up. We point our browser, pretty much any browser, to this URL, and what we see there is a Mars base map. So we've got the globe. This is all we needed to do, that one command and the JSON file to actually have a browsable map, and we can take a look around. We can take a look into use Casma and see what it looks like. Next thing is that we add nomenclature. We go back to our JSON file, and to that JSON file, we add a free layer, so-called geodata free layer, which includes the nomenclature. That's another public resource, so we're making use of that Mountain Technologies made all this data available. And we just add it to the JSON file. There's one optional step that I won't be describing here, which is that we can make the nomenclature searchable. The tutorial how to do this, how to have a search window where you can actually enter the name of the feature is available online, so you can refer to it. Anyway, once we do this, the map has become a bit alive, and we see all these labels. There's about 1,500 of them. And this is the official International Astronomical Union nomenclature of the planet. And we can type use Casma into the search window, and we will be kind of teleported there. Next thing is that we add the Mars Express HRSC data. So we download the two data sets. The first data set is the orthophoto imagery. The second data set is the DEM. So we download these two. Consequently, what we do is that we set up a VTS MapRoxy tile mapping service from the orthorectified matter image, and we set up a VTS MapRoxy triangle irregular network service from the DEM. Now, the process to do this involves multiple commands, and I invite you to check that accompanying site to actually see how to do this. Once we do this, what we can do is that we can take a look at our MapRoxy introspection API and see the tile mapping service that we created from that orthophoto image that we downloaded. And now everything went black. Okay, yeah, I don't know why, but okay. But I'm getting ahead of myself a little bit here. Yeah. So this is the first video I was going to show you. This is the tiled mapping service, which is visualized here in leaflet. So MapRoxy, what it does for us is that it converts that single image into the hierarchy of tiles, and we can see what the image that we downloaded actually is going to look like. But it gets more interesting once we take a look at the second URL, which is here, and this URL actually shows us the TIN service rendered here in the VTS browser.js with the orthophoto drip over it. And now we get a very detailed view of that 75 kilometer wide section cutting through the use Casma, including the West Coppertest Montes, which is the area that we want to have mapped. Next, we move to the high-res data. Once we have it's pretty much identical approach. We have two data sets. One of them is again the orthophoto. The other is the DEM. We do the very same steps with them. We set up a VTS MapRoxy TMS service and the VTS MapRoxy TIN service. The first one from the orthophoto, the second one from the DEM. Once again, the details are available on the side I was pointing you to. And we inspect the result, and now we're really seeing the small section of Coppertest Montes at this extremely high resolution I was talking about, which goes to 0.5 meter in terms of imagery and to 2 meters in terms of geometric precision. It's a very small section of the surface, but it comes in this visual detail. Now the fun part really comes now. We put all these resources together and make them a single map, which should provide something like virtual reality experience in the end. So this is what happens. We run these two commands, and basically we just use the VDS command line tool as its data fusion capabilities to add the HRSC and high-rise tin services that we created as part of the map proxy into the VDS storage. We perform these two commands, and after we run them, we go back to our storage view and say, we want our map to include all these resources which are now available in the storage. So we say there are 3 tile sets. The first one is the global DEM covering the entire planet. The second and third are the HRC and high-rise data. And we say, and we want to have these 3 order photos in hierarchy, wrapped over the terrain. And this is pretty much it. We go back to the URL where we started when we inspected the base map, and we can see some pretty stunning images of the Martian landscape. You can see it all integrated. You know, this is the global view. Then there is the more detailed HRC data and the very detailed high-rise data. So this is the map that we've created, coming all the way from the planetary scale to this level of detail. And if we actually processed every high-rise image and every HRC image, which is something that somebody will, hopefully one of you might be doing one day, then we might be getting the most detailed map of Mars ever created that's going to reflect on our current state of knowledge. We have just a few minutes left for our second case study, so I need to be a little quick. Our second case study is more difficult and easier at the same time. What makes it easier is that there's just these 2 data ingredients: the New Horizons Global Mosaic and the New Horizons Global DEM, both coming at 300 meters GSD. This is actually fairly new data released by the Johns Hopkins University Applied Physics Laboratory just 1 year ago. And that's what makes it easy. What makes it difficult is that, unlike Mars, which is known to VDS and parts of its configuration, Pluto is a totally unknown object. So we need to go through the process, which is called the reference frame definition. That's a fairly complex thing to do, and I don't really have time to cover it in much detail. But basically, this is one of the New Horizons images taken as the probe departed from, and it showed the dwarf planet Pluto backlit. So Pluto is fascinating in that it's one of the few objects in the solar system that is known to have atmosphere. And we kind of introduce our knowledge of it to VDS, and we start by defining the celestial body itself. We name it Pluto, and we say that the atmosphere is runs to about 200 kilometers. That we kind of estimate the visibility, take a very empirical approach from the images we're seeing and the colors that the atmosphere might be having. We define the spatial reference systems that we're going to be needing in the reference frame. The geographic spatial reference system, which, as you can see, is using the brush reference of an object that's about 1,188 300 meters, which is the measured size of the radius of Pluto, which is a spherical object, corresponding geocentric system, and also the projected systems which are going to allow us to define our tiling. And finally, we define the reference frames, which is going to make the entire object known to VDS. And then we can inspect it using the MapRoxy system tools. What you're seeing here is not the logo of the next Football World Cup. It's actually the way VDS chooses to communicate to you what the tiling scheme is going to be for the object, for the planetary object that we've just defined. Then, you know the drill. We download the data set. One is the DEM, the other is the orthophoto. We set up a MapRoxy VDS, MapRoxy TMS service from the Mosaic, a MapRoxy TIN service from the DEM, and then we just take a look at it. And if you remember, that heart on Pluto image that I was showing you is, well, this is what we have achieved, and it's the same image, but the difference is that it's not an image. It's actually a browsable three-dimensional map of one hemisphere of the planet. The New Horizons mission was a flyby. It was not an orbital mission. So basically, we just know one hemisphere of Pluto. But still, it's pretty amazing that we can actually use this data to explore, for example, these icy volcanoes, which were one of the most amazing discoveries made by New Horizons on the fairly young geologically young surface of the planet. And you imagine that 3 years ago, like all this was, even in our most powerful telescopes, it was nothing but a smudge. And this is what we are seeing right now. So this is it. Remember, the live demo of both case studies is available on this address. I've also included some links on further information on VDS if you find it interesting. And there's also 2 related VTS tutorials online, which are called the Peaks and Valleys of Mars and Mars Part 2 Searchable Nomenclature. These 2 tutorials can be used by you if you intend to do your own mapping project with celestial bodies and VDS.
Thank you. Any question? No? I have just one doubt related to your data. All the data that you used were free downloaded, or you have to make some protocol with NASA, ESA, or something?
Well, actually, all the data is available freely. Well, we did one minor change to them, which means that we converted grayscale images to panchromatic images for more visual appeal. But it's a fairly easy thing to do, which I'm sure anybody can do with GDAL pan-sharpen or a similar tool. So yeah, all this data is available for free from those sources that I was pointing to at the beginning.
Okay.
Yes, please.
Can you repeat, please?
Yeah, the microphone.
Thank you.
Okay. What about celestial bodies that are not spherical shaped? For example, asteroids. If you can reconstruct a 3D model of the asteroid.
Yeah, it's if you can define an ellipsoid for it, then it's going to work. If you have totally probably an ellipsoid and the torus. Those are the topologies that we'll be supporting out of the box in VDS. So if you can, you can model asteroids and comets without the limitations. But if you wanted to model something that would have totally irregular shape and could not be approximated by ellipsoid of any type, then you'd probably need to dig a bit more into the VDS data model to do that.
Okay, thank you.
Thank you. More questions? No? Thanks again to all the presenters for this session.
Thank you. Thank you.